1106, The Safety Factor, from GBH TV Boston and the BBC.
Major funding for NOVA is provided by this station and by other public television stations. Additional funding is provided by grants from TRW and the National Science Foundation.
Ready for takeoff?
Ready here. Ready here.
And say to takeoff checks complete.
Okay, here we go.
A multi-million-dollar machine controlled by 3 highly skilled airmen.
80 knots, both sides.
The mission, to carry 345 men, women, and children through the sky in safety.
Fire warning number 1.
Abandon. 110.
Spoiler deployed.
100 knots. 80 knots.
90%.
60 knots. Confirm the defect. Engine fire number 1.
Okay. Checks.
Engine fire drill.
Okay.
Throttle to idle. Fuel
Idle.
lever to off. Lift off. Engine fire handle.
It's pulled.
Agent discharge.
An engine fire is a rare event, but they must know exactly what to do.
And the fire is out of the checklist, engine fire checklist.
So every 6 months they go to school to practice in a simulator what they may never experience in actual flight.
Okay, Harley, let's do a normal takeoff this time, shall we?
Upon such elaborate games depends our safety in the skies.
Okay, ready for takeoff? Ready,
sir.
Steve James, senior training captain for Laker Airways, has come to the American Airlines Flight Academy in Dallas, Texas, to fly this sophisticated simulator. It feels and sounds and handles just like a real DC-10.
V1. Rotate.
But it allows the pilot to try things he'd never risk in real life. Steve James.
There are things that could happen, but don't often happen in the actual aeroplane. To practice some of these maneuvers on an actual aeroplane would be, well, gross stupidity. For example, the abandoned takeoff, the rejected takeoff, one would never dream of doing that on an actual aeroplane because you would actually damage a very valuable piece of equipment. You're talking about at least 8 tires having to be completely scrapped, plus possible damage to the wheels and the brakes.
We're now 10 years into the era of the wide-bodied mass transport jet. October 15th, 1979, Gatwick Airport outside of London. To see how the safety factor has become a part of every routine, we'll follow Steve James and First Officer David Field on a flight across the Atlantic to Los Angeles.
GK1 to Bangor.
Their day begins with a visit to the meteorologist. They set their margin of safety by the strength of the wind that westbound will be against them.
Actual takeoff weight is going to be 408.
Distance, wind speed, and payload give their fuel required.
99,000 pounds.
Check.
Which means that putting up the contingency fuel from the basic minimum.
For any aircraft, the weather or some emergency could force it to alter its course. But for every 5 tons of contingency fuel carried across the Atlantic, they'll need an extra ton just to get it off the ground. There's a balance to strike between safety and economics. The mechanical condition of the aircraft is the responsibility of the 3rd crew member, the flight engineer, Jim McLaughlin. The walk-around is to double-check the obvious, to ensure that all the hatches and openings are closed and locked, that every fastening is secure.
Good morning. It's the flight plan Laker 1 to Bangor.
Thank you.
Meanwhile, the first officer files a flight plan, a detailed account of our journey that's transmitted immediately to every air traffic control center along our route. A computer west of London disgorges the data that will place our safety in the hands of others, who will monitor our progress from the ground. To every controller from here to Los Angeles, we are GK01. The Los Angeles-bound passengers have their own concerns: the cost of a ticket, the time they stand in line. The airlines prefer to advertise their advantages of price and convenience. But when accidents hit the headlines, they remind passengers of the risks of flying. In fact, mile for mile traveled, the risks are modest. In most countries, rail transport has the lowest accident rate. Commercial aviation kills more people per mile. But on the roads where our lives are in our own hands, we tolerate a much higher toll. Nothing we do is without risk.
Cockpit preparation checklist, please, Dave.
But we expect these professionals, to whom we entrust our lives, to keep it as low as possible.
Hydraulic flight control lights.
Off.
Flap limit selector.
Auto.
Elevator field selector.
Auto.
20 minutes before takeoff, the crew goes through its final checklist.
Engine instruments.
Checked.
Flaps to that position.
Each check involves two people. The words must be spoken. The routine never changes unless an answer is wrong. Then it could hold up the flight. Today, our DC-10, called California Belle, is less than half full as she travels to Los Angeles, with a stop to refuel and a change of crew en route.
Excuse me, Steve. All the passengers are on board 164 and all the ship's papers, and we're ready now.
On apron or taxiway, for every move, they must have permission.
Take one after the landing 111, line up and hold.
Ladies and gentlemen, we're approaching the runway for an easterly takeoff.
For Steve James, his most dramatic event as a DC-10 pilot has been just one precautionary engine shutdown in flight. A pilot can spend his whole working life preparing for emergencies that never happen.
Checks with the car. Cabin reports has been received. PA, just hold it there.
Laker 1 cleared for takeoff. Standard right, turn out the surface wind is 210 degrees, 7 knots.
Now they drive over 200 tons down a bumpy runway, steering it like a bus.
Airspeed both sides. 80 knots.
Offset, check.
At this stage, they can still abandon the takeoff, as they did in the simulator.
Rotate.
Negative.
Now, if an engine fails, the aircraft should still have enough power to climb safely away.
Thank you, Laker 1, contact London 1284.
From this point on, they dial in course and altitude, and the aircraft flies itself. Their job now is to monitor and check.
Time checklist. External lights.
That's
Yeah.
required. Flap lights out.
Flaps and slats.
Quadrant gauge check up, retract.
Spoilers.
Disarm.
Meanwhile, the controllers in West London must keep us separated by height or horizontal distance from all other aircraft.
Laker 1 heavy, Roger, no speed restriction, climb to 5,000 feet.
Our position is revealed by radar, and our call sign and altitude displayed to the controller, whose job it is to guide us through this dense pattern of traffic.
I've done that, Roger.
Laker 1 right heading 340, climb to flight level 120. All right, 340 up to 120, Laker 1.
He's given us a new course and altitude. The complex procedures designed to ensure our safety do not concern the passengers. For them, the question is simpler. Is flying safe or not? They know that this particular type of aircraft, the DC-10, was in 1979 involved in an accident that caused such a crisis of confidence that every DC-10 throughout the world was grounded. When an engine broke away on takeoff, it tore through hydraulic control lines and one wing stalled. The crash was attributed to faulty maintenance, but the design of the engine mounting didn't help. And there have been other disasters since. Even a minor problem can make a headline.
But I think actually we profit as a result of these things, and we're far safer today than we were maybe before some of the other tragedies that happened.
Well, I was a bit worried, but now, since I got on the plane, I'm not worried at all.
Yeah, I would say that when the DC-10 got grounded and recently about the DC-9, it kind of gives you a little, makes you think a little bit.
You know, I just have a lot of confidence in them, and I don't mind flying DC-10s at all.
I think there's more danger on the roads than in the air.
For a company like McDonnell Douglas, the stakes are high. 5 years of effort went into designing the DC-10, and over 300 have been built at a current cost of $40 million each. Here, they're proud of their product. How do they react to the recent accidents? In charge of design, Vice President Gene DeBille.
After any accident involving a Douglas product, it is a real shock. It sets you back, it affects your sleep, it affects my sleep. You can ask my wife, she'll tell you it is something that you have to live with. You have to certainly get at the root of the matter on what caused the accident. But we do recognize, I recognize when I came into this business that, you know, it's impossible to be involved with the product that moves, that someday isn't going to have an accident.
At the time of our filming, there were 5 Laker DC-10s on a busy production line, a longer range model with more powerful engines to carry extra fuel. Each aircraft is a structure of enormous complexity. In the nose alone, there are 55 miles of wiring radiating out to the nerve center of the flight deck. Yet this sophisticated machine is a handcrafted product. The whole wing is a fuel tank. Inside the trailing edge travel the cables and hydraulic lines that control the ailerons, flaps, slats, and spoilers. Most come in duplicate, even triplicate. It's known as redundancy. If one system fails, another is supposed to take over. Components and sub-assemblies are made all over the world, but put together here at the Douglas plant in Long Beach. 2 vast barrel sections of the fuselage are being joined end to end. There's no overlap, just a plate riveted on the inside to lock them. The redundancy of the hardware must be matched by human redundancy. There's supposed to be a careful record kept of who did what throughout the aircraft and who checked it. This Douglas inspector uses a feeler probe to check for any gap. Here the craftsman records that he has completed his job, and the inspector buys it. For any new aircraft type, the manufacturer must submit a vast library of performance and test data before the Federal Aviation Administration will issue a certificate of airworthiness for the plane to carry passengers. Still, the accidents occur. Near Paris in 1974, a Turkish DC-10 with a design problem known to both Douglas and the FAA crashed, killing 364 people. An inadequately designed cargo door had blown out, an interior floor collapsed, and control lines ripped away. Now the door lock has been redesigned, the floor above it strengthened. 20 months before the Paris crash, there was an almost identical cargo door blowout, but the pilot landed safely. Why did it take the Paris crash to get the level of action needed? Former Director of Aviation Safety at the National Transportation Safety Board, C.O. Miller.
Well, I hate to oversimplify it, but history has shown that the major accidents are the biggest single motivator towards changing standards for improved safety. I think that's an indictment of all of us because we like to think we don't have to wait for that, but I'm also sorry, I will reiterate that I think history has told us that's not the case.
What recent history also tells us is that accidents are no longer simple events with a single cause. They result from a complex combination of circumstances, usually involving many people.
Liquor 1, you cleared flight level 310.
Here, our flight, GK01, has been skillfully guided through the dense thicket of traffic over southern England and is now climbing to the altitude at which it will use least fuel. Now we must be fed into another system of control which governs flights over the Atlantic Ocean.
Liquor 1, your routing is Belfast, 55 north, 10 west.
Each day, the controllers in Scotland and Newfoundland study the pattern of wind and map out a set of 9 highways across the ocean. From Belfast, we plan to take Track Charlie, 3rd from the north. But there's already traffic there, so we get offered the next one south.
Okay, we'll accept Track Delta, flight level 340. Okay?
It's one track south.
It's all right.
Yeah.
We haven't got much choice, really, have we?
Not really.
Track Delta.
We'll take 36 if that's available.
The flight engineer wants 2,000 feet more height if the controllers will allow it. It will use less fuel and increase our reserve for emergencies. As we head out over the ocean, he's already noted one small technical defect. One of the instruments recording engine revolutions has an anomalous reading, but they're satisfied that only the instrument, not the engine, is at fault. It's not a defect that requires us to return. So the flight engineer notes it in the technical log to be corrected later by a ground maintenance crew. Again, a balance to be struck between safety and the urgent need to keep planes flying and so paying for their keep. A license to run an airline doesn't allow a company to set its own standards. The regulating agency must approve procedures like maintenance and see that they're properly carried out. At Laker, the inspector from the British Civil Aviation Authority can drop in any time and take a look for himself. This is a method of detecting damaged turbine blades without taking the engine apart. But here there are so many airlines that the FAA often has to use representatives from the companies themselves to inspect their own procedures. Maintenance can also take advantage of information on the performance of the aircraft and its engines carried by the flight data recorder. In the DC-10, it's located just inside that rear cargo door. The data can help save money by sparing them unnecessary work when all is going well. Originally put here as a crash recorder, it's kept inside an armored, fire-resistant box. The airlines are legally required to report certain mechanical defects to the FAA, but the manufacturer, too, has an interest. At Douglas, this is a rack of what they call service bulletins, changes that the manufacturer has advised with varying degrees of urgency. If there is a marked safety implication, it becomes an alert bulletin. This one deals with corrosion on a cargo door bolt. A telex is sent from Douglas listing serial numbers of all affected aircraft and telling the airlines what to do. One stage stronger is a compulsory airworthiness directive issued by the FAA. This goes on all the time, not just after accidents, and for all aircraft types, not just our own DC-10. We're 2.5 hours out of London. To tell us where we are, we use a navigational computer independent of outside signals that's accurate to a few tenths of a mile.
That's our actual updated position. That's the track is 274. Our ground speed is 390 knots. It's going to take us 50 minutes to reach 40 west, and the wind at the moment is 279 degrees at 91 knots. So we've got a headwind of 90 knots.
Lunchtime, and the rule is the captain gets a different meal from the first officer. That's in case one of them gets food poisoning. Good health is a condition of a pilot's license to fly.
Kitchens have done themselves proud today that the medical examination for a pilot is every 6 months. And this is very, very rigidly enforced. In other words, if one doesn't have a medical within a 6-month period, then one's license becomes invalid. To a certain extent, the checks become a little bit more rigorous as one gets older. So over the age of 40, for example, one has to have an electrocardiograph every year.
The medical tests go into his license along with his records of training. But what if a pilot does become incapacitated at a critical time? It doesn't happen often, but it did happen in 1972 to a British Airways Trident climbing out of London Airport. Since this crash, they now practice how to deal with a pilot who's collapsed. Like most accidents, this one had a combination of causes, partly mechanical, but mostly human. In fact, as aircraft become more sophisticated, the proportion of accidents caused by mechanical faults is falling. As carefully trained as pilots are, the proportion of accidents attributed to human error is on the rise. At the Airline Pilots Association in Washington, D.C., John O'Brien.
I think a review of accident statistics will probably show that 80% or maybe more of accidents are attributable to human error, pilot error, you may want to call it. And we won't argue that point. We'll accept that point, that that's the way that the accident has been attributed. The question we always ask is, why did that human make the error?
In 1974, a TWA 727 on approach to Dulles Airport near Washington, D.C. was flying too low and hit the side of a hill. But that human error might not have occurred had the pilot known that the same thing had almost happened in the same place just a few weeks before. And that's not uncommon. C.O. Miller.
I don't think I've ever seen an accident in my career since maybe the first 4 or 5 years of my experience that I couldn't name a previous accident, a precursor event, if you will, from my own recollection, let alone researching it.
The search for incidents that might be precursors to accidents led to a new kind of reporting system set up by NASA at Moffett Field in California. Each morning, Bill Renard collects his mail. It's a kind of confessional. Nobody has to write to him. It's all completely voluntary. The intention is that pilots, controllers, and other airline staff will share their experiences, even their errors, as a way of helping others avoid the same mistakes. The aviation safety reporting system is confidential. We were not allowed to show an actual report. This example is made up, but it's typical of the 5,000 to 6,000 they receive each year. Human errors like air misses, near collisions are high on the list, and the explanations may be more candid than would be given in a public inquiry. Dr. Charles Billings, a founder of the system, hopes to spot trends and recommend changes before the real accidents take place. But why not simply punish the wrongdoer as an example to others?
Since pilots, like the rest of us, are human, they do make mistakes. I think it's far more important to get the details of those mistakes out on the table, where we can examine why the mistakes were made and hopefully correct the system in such a way that the system at least does not provoke those errors. I think it's far more important that we do that than that we punish an individual for being human.
In Britain, the Civil Aviation Authority set up an occurrence reporting system following the 1972 Trident crash. Unlike ours, it's mandatory and includes both human error and mechanical defects. Steve James.
An incident or occurrence which justifies filling in an occurrence report and has to be completed within 24 hours and transmitted back to the operating company, and from there transmitted to the Civil Aviation Authority, who collate all these reports. The idea being that the information that is collated is then disseminated again through the industry in order that everyone may gain from other people's experiences.
The British system is backed up by a helpful piece of hardware which a few airlines are trying out. In this DC-10, down below the flight deck in what is called the avionics compartment, is a quick access recorder. It has the same information as the flight data recorder, but it's easier to get to. This is 8 seconds of digital data, or it can be converted into easy-to-read graphs. This kind of data is intended to help the authorities learn how to interpret the more descriptive pilot reports.
35 for
35 for 19.
We've reached the most critical phase of the flight. We have crossed the Atlantic and are descending to land and refuel at Bangor, Maine. Even an airport like Bangor, not heavily used by the airlines, can be busy. There's no shortage of light aircraft, and safety means looking out the window.
Cessna 975, your traffic's mid-bill on left downwind, report him in sight, it's an AVP 3.
Laker 1, roger, cleared visual approach runway 33. Contact the tower 120.7.
The gear down.
Ready to take off.
We're in sight of the airfield.
Laker 1, heavy, Bangor Tower, clear to land, wind 280 at 10.
That heavy is a designation for all wide bodies and 4-engine jets. Half of all accidents occur on approach and landing. We're so close to stalling speed that a sudden change in wind or a small misjudgment of height or distance could cause disaster. Even after touchdown, the condition of the surface could cause aquaplaning. We could skid off the runway. Laker has chosen to refuel at Bangor because its runway is long enough and is less congested than the other East Coast international airports. Congestion cuts down the margins of safety. Pilots and controllers are faced with the choice of reducing separation between aircraft waiting to land or take off and wasting precious fuel in order to space them out. There are rules defining separation, and one of them is that after a heavy like us, there must be a gap of 5 to 6 miles. Technology and the economics of mass transport have made wide-body jets profitable for the airlines, but it hasn't increased airport capacity to the same degree. They'd like to pack more in, but that means danger. A simple demonstration shows how. Here at NASA's Langley Research Center, they use a scale model of a DC-10 and a wind tunnel to study effects which all aircraft produce.
Transmission forward, run.
White smoke makes visible the whirlwind wingtip vortices that trail in our wake. The larger the aircraft, the more powerful the effect. A medium-sized plane like a 727 could be flipped on its side dangerously close to the ground. A lighter aircraft like this Learjet could be overturned completely. Besides increased separation, what can be done? At NASA, the best answer yet is to land with the spoilers up. These are raised surfaces that break up the airflow. This does reduce the vortex by half, but it also reduces lift, and so you have to land faster. The margin of safety for the heavy aircraft goes down, and that's a trade-off they're unlikely to accept. A danger that no one can avoid is the fuel itself. To get across the continent to Los Angeles, some 47 tons of fuel are needed. Even with this hose, it takes 30 minutes to load. Before takeoff, both wings will be completely full. At Bangor, there's a new crew. It's a question of permitted flying hours. This extra crewing means considerable financial loss to Laker and will change as soon as the new longer-range DC-10s are ready. One less landing, one less takeoff will also reduce the wear on the tires, the stress on the airframe. There's one more precaution to be taken by the flight attendants. The emergency escape slides are armed, made ready for instant automatic inflation.
On behalf of Captain Richardson and his crew, I would like to welcome you back on board. Once again, I would like to draw your attention to the safety instructions for this aircraft. We would ask you to read this carefully. You will notice the emergency exit.
The first-time passenger who nervously reads the instructions may have a better chance of survival than the seasoned traveler who shows sophistication by ignoring the safety demonstration.
Sufficient individual oxygen masks will drop.
This is what the flight attendants are here for. As a legal requirement for safety, there must be one of them available to man each emergency exit. A quarter of all major accidents occur on the takeoff or the climb out of the airfield. We now have that heavy fuel load. And in the last year or so, load factors have been going up. With more passengers and more cargo, aircraft are flying closer to their designed limits. Even half full, now that we've taken off, we're far too heavy to return safely to the runway we've just left. In an emergency, we'd have to use up or simply dump 25 tons of fuel to get down to a safe landing weight. But supposing we did crash, what then? Nobody wants to think about it, unless it's his job. Today, you just can't afford to go around crashing jumbo jets to see what happens. But at NASA's Langley Research Center, they were fortunate enough to inherit 34 flood-damaged light aircraft for a study of crash survivability. The forces on the occupant, the seats, and the airframe itself, under a range of different crash conditions.
Operations 2, this is Operations 1. We're ready to roll the aircraft now.
One conclusion might be, don't crash in a light aircraft. But are your chances any better in a big jet? At the FAA Civil Aeromedical Institute, Dr. Robert Dilley.
Yes, a commercial airliner is actually a very survivable vehicle. It attenuates the energy very well through deceleration, through the landing gear, the wings, the crushing of the cargo compartment. And it's not unusual to find a what would look like a serious accident with which none of the passengers have had any real significant impact injuries.
They use anthropomorphic dummies, as they're called, to tell us whether we can survive the crash. Costing $12,000 each, they're instrumented in head, body, and limb to register the forces of impact. Here they're interested in the flight attendant and her seat restraint, since it's up to her to help the rest of us. They're assessing a 4-point system that some new aircraft already have. In this test, the impact forces on her will be 9 times her own weight.
Stand by. 9, 8, 7, 6, 5, 4, 3, 2, 1, fire.
Telemetry and the slow-motion camera reveal that she would have survived to help her passengers, none of whom today is provided with a seat belt so effective as this. Dr. Dilly.
Our staff has participated in accident investigations since 1961, and we regularly see accidents in which there are no impact injuries, but in which the victims suffered from a post-crash fire and what we have found to be combustion product toxicity from these fires.
In 1973, a lavatory fire aboard a Brazilian 707 caused it to make an emergency landing at Paris Airport. The flight crew survived, but all the passengers were dead, apparently overcome by the smoke and toxic fumes from the burning cabin interior. The materials used in aircraft cabins are studied at another FAA research center near Atlantic City, New Jersey. To gain rapid experience of what might happen in a variety of different fires, they use a Porter-scale model. The record shows that the most common hazard is what's called a pool fire. Fuel spilled and ignited to blaze outside the crashed fuselage. This raises a whole string of questions. Will the cabin itself be set on fire? What about the materials there? Will they give off such deadly fumes that passengers will be too incapacitated to save themselves, even if the fire is put out? Current standards for fire resistance don't take into account the intense radiant heat that you get in a well-established blaze. Even so, the provisional results of these model tests are that in comparison with materials, a far greater hazard is the pool fire itself and the smoke and carbon monoxide that will enter the cabin. One answer has been the choice of fuel itself. This one is not easy to ignite. We eventually got it going with a propane torch. Instead of JP4, a cheaper fuel widely accepted until a few years ago, all American and British airlines now use this Jet A kerosene. This flame spread slowly, but within 90 seconds was burning well. And that 90 seconds is the basis of the current standard for aircraft evacuation. At the FAA's Aeromedical Institute, they're investigating some of the problems the passengers might face. They have paid volunteers and a fuselage that tilts to mimic the effect of a collapsed undercarriage.
Okay, if everyone's ready now, when we get inside the simulator here, you will be wearing smoke goggles. Linda will pass the goggles out to you from the edge of the building here as we go onto the simulator.
To get the effect of smoke, they use frosted goggles. And when the main power shuts off, the emergency lights will be dim.
A warning bell will sound to start the test. When you hear the bell, do as you're told.
Unfasten your seatbelts and come this way as fast as you can. Let's go. Come on, unfasten your seatbelts. Let's go. Get out of here. Come on, let's go. Come on.
Despite the difficulties, these volunteers got well trained during our filming, which is fortunate for them, as some flight attendants have claimed that with a plane load of people, only trained subjects could all get out in 90 seconds. And there's worse. In another test, they simulated a handicapped person who had to be helped.
Let's go. Come on, everybody. Let's go. Get out of here. Hurry up. Let's go.
During the time the aisle is now blocked, 10 healthy people could have gotten out. That's 10 people who could lose their lives while one is saved. So brutal as it sounds, there's a rule that no one tells you. Healthy people first, because that saves more lives. The quarter-scale model shows what happens with real smoke. It's hot, so it rises. It stratifies. Here you'll do better to crawl out, so long as you know which way to go. One idea that's being tested is low-level emergency lighting in the armrest. But this would cost money, and it hasn't yet been accepted.
Faster, come on, move it. Let's go. Get out of here. Come on, faster.
The hard fact is that in a fire, you've desperately little time, and everything is against you. You can't see, you can't breathe, and in the real smoke from a pool fire, there's so much carbon monoxide and other fumes that 90 seconds is a deadly realistic limit. Dr. Dilley.
One concept that we followed back in the early 60s, when this first became apparent to us, was to conduct research to determine the feasibility of providing an uncontaminated source of air for the passengers to use for the duration of an emergency evacuation. It's a smoke hood. It will not burn. It will not melt. It will char at 1472 degrees Fahrenheit. It's very compact in stores. It's very easy to don. One can see through it very readily and converse through it. Has an aluminized metallic top, which gives 90% reflectance of infrared radiant heat. We don't think it will cause panic. We don't think it will cause a delay in the evacuation. So, depending on physical activity and ambient temperature, you can wear this for somewhere between 2.5 and 8 minutes. It's comfortable enough that I keep tending to blow out the match, and of course that doesn't do. The original suggestion for this was to come up with a super sick sack of sorts that somebody could wear and could be stored in the seat pocket in front of the individual.
However, this was not accepted either. But you could be lucky. When a Continental DC-10 ran off the runway in Los Angeles and ruptured its fuel tank, all but 2 passengers were evacuated safely. The wind direction was in their favor. But it took 5 minutes, not 90 seconds, because one of the escape slides burst and deflated, and others burned in the fire. This is a test of 2 inflated slides. They cost about $12,000 each. A metallic heat-reflective coating would delay a collapse, but would add to the weight and cost. So it's another idea that's not yet been accepted. But in some accidents, you don't get a chance to use the slides. At Tenerife in 1977, in poor visibility, 2 Boeing 747s slammed into each other on the ground. 583 people died in the blaze that followed. Even with today's supposedly safe fuel, there's one further problem. Here's a demonstration. It uses just one of those barrels of Jet A in a tank shaped like a section of a wing high above the ground. Air is blown over it at more than 100 miles an hour. The fuel is thrown forward into the airstream. There's also an ignition source. The result is due to an effect called misting. In the form of tiny airborne droplets, the Jet A went up like a bomb. Misting has been known for a long time. At Lakehurst, New Jersey in 1973, they thought they had the answer, an additive that turned the fuel in the tanks to jelly. It wouldn't explode, or so they thought. It was a classic case of back to the drawing board. But not much was done until Tenerife shook the industry. Then enthusiasm began to grow for a British product, a fuel modifier called FM9, or anti-misting kerosene, AMK. There's ordinary Jet A on the left, and the modified fuel on the right. It's turned into long chain molecules that will stick together. At the same 100 miles per hour, this test of AMK worked well. So in a cooperative development effort, the US and Britain are now studying how well it works in the engine. If successful, the two countries will go together to the International Civil Aviation Organization, ICAO, to urge that it become the industry standard. But there's one problem. It makes fuel more expensive, about 2 cents a gallon. It will increase the cost of flying. Even thinking about this changes the emphasis of flying. The moment you mention safety, the passenger is bound to think of danger. It's generally thought that a mood of eat, drink, and be merry sells more tickets. So the flight attendant, whose real job is safety, spends most of her time as a waitress. The dilemma is this. The industry is being asked to provide additional safety measures against extremely rare events. It's very expensive, but it's been estimated that over the next few decades, the fuel modifier alone could save 10,000 lives. Changes on the flight deck are easier, and some are getting to be necessary. Increasing complexity and new requirements after particular accidents mean that the pilot is surrounded by warning systems. Too many, some people think. In the next generation of aircraft, it will look something like this. The electronic flight deck with information processed by computer, which allows you to concentrate your attention on the things you really need to know.
Okay, we're going to accidentally lower the flaps to get a speed over speed case. Okay.
In this simulator, the pilot has accidentally lowered the flaps at a dangerously high speed.
And the right picture.
In addition to the alarm, a display of the control surfaces shows exactly where the trouble lies. The pilot has new kinds of navigational maps or the familiar compass displayed as he needs them.
Place on the map.
This example from British Aerospace would replace most of the conventional instruments by 7 monitors and new warning systems, which start off by telling you where to look for information. This time it's a hydraulic failure. To find out what to do, you have a checklist. But here it's not just a piece of paper. It's programmed into the system, and you press buttons to run down it. But it's still the pilot who must take the action. The point is to use the computer to calculate and present options, freeing the human to exercise judgment and make the decisions. Another line of development is shown aboard an aircraft originally funded as part of the ill-fated SST program. It's an unusual kind of plane. You may think it's being flown by these pilots up front on the flight deck. You'd be wrong. Hidden away inside, its windows covered, is a second research cockpit. Backed up by a team of scientists and engineers, it's the pilots here who really fly the plane. Here, too, there are electronic displays. Below the altitude indicator, a navigational map. It tells the pilot where he is and where he should be according to the flight plan programmed into the plane's computer. They call it flying the box. The little rectangle is where he should be. He has to keep the triangle, the aircraft, neatly inside. The purpose of this research is to fit more aircraft, or the same number more safely, into the limited airspace that exists around airports. It should also save fuel and reduce noise on the ground, which you can't do today without a safety penalty. So pilots don't like noise abatement. If you approach an airport on instruments today, you must fly straight down a narrow beam extending many miles from the airport. The beam is generated by an instrument landing system, an ILS antenna at the end of the runway. But at Atlantic City Airport, the FAA is testing a newer system called MLS, the microwave landing system, which all major airports will have in a few years. 2 transmitters fill the space before the runway with a grid, and aircraft equipped with a special receiver will be able to approach the runway from many different directions. The NASA aircraft has been testing it out. The pilot is now going to land, but on a curved approach. The flight plan takes us over 2 beacons off to the side of the airport. Now, as the pilot banks the aircraft, the dotted line shows the path that he's on. He has to match the curves. He's still flying blind. The tip of the triangle is just a second or 2 ahead of the box.
Enable at 1670.
On the upper screen, the computer generates a perspective view of the runway he's approaching. In the top right-hand corner, his height. In fact, he does have a television camera on the outside of the plane to let him know how accurate that is. And the real world is right where it should be.
Okay, I'm going to go flaps 30.
MLS will happen in the next few years, but flying the box is still an experiment.
We've got D2. ILS 25 black, decision height of 200 feet and an altitude of 300 feet. 200, 300.
In today's real world, life is a little more complicated, for the pilot anyway. We're now nearly 14 hours out of London. In this second leg, the aircraft has been passed from one control center to another. Now we're under control of the Los Angeles Air Traffic Control Center, for security reasons actually located out in the Mojave Desert. And within the center, we are handled in turn by 3 sector controllers.
Laker 1, Connect Los Angeles Center 133.55. So long, sir.
Now, Laker 1, it's pre-cleared 240, pilot's discretion at 280.
Our flight, Laker, or GK1 in the center of the screen, is well separated from other commercial traffic heading west to Los Angeles Airport. Along the coast, all those smaller symbols are other aircraft, including military and light planes flying among the 10 major airfields in the Los Angeles area. What if one of those were to trespass into our protected space? In 1978, this PSA plane failed to keep a light aircraft in sight. 144 died. With over 200,000 aircraft in the United States, only a small proportion large airliners, the skies may be overcrowded. John O'Brien.
The mix of traffic and the density of traffic is such that the potential of mid-air collision is increasing. And in the opinion of the air carrier pilot, the only solution to that is an airborne collision avoidance system.
It works like this. The aircraft radiates a signal giving its altitude, course, and speed. Danger. The signal comes back to the original aircraft, which is advised to dive. A system is already being developed. Move on a little, and the other aircraft will now pass overhead. The advisory changes. Don't go up. The pilots may want control, but there's competition from the ground. It's a 20-year program, over $1 billion, to tie collision avoidance into the ground-based air traffic control system. Each station uses 38 mini-computers hooked together to calculate and predict all potential conflicts. The flight deck, 10 years from now, has its electronic display. Most of the time, it shows things like a radar picture, a weather forecast for where it's going, or a weather map that's sent up from the ground. The ever-vigilant computer system keeps everyone in sight. The air traffic controller does nothing. He merely observes as the conflict develops. Here, two aircraft are flying towards each other. At a certain point, the system is triggered. The computers determine a course of action that's safe for all the aircraft around. On the flight deck, the signal comes up automatically and exclusively to the aircraft involved. Here in the circle, it says, "That's you." Up here and closing fast, the source of danger. And to know what to do, look down here. Turn right and limit climb to 500 feet a minute. This conflict will now be averted. When all this is working, the problem posed by the PSA midair may at last be solved. But we can predict that there will be more collisions first. This system won't be complete for years. Three lights in the sky above Los Angeles. And 164 passengers' lives are being delivered to their destination in almost certain safety. But how safe is safe enough? Can we reasonably demand or hope for zero risk? C.O. Miller.
The concept of not being willing to accept any risk at all is ridiculous to me. Because, first of all, we don't do that in any other part of our human endeavor, whether it's walking across the street or whatever it is. I think the thing that upsets the public is not knowing the factors. They don't know what the risks are.
What the public and the industry must accept is open discussion of the risks and recognition of incidents and occurrences, the accidents waiting to happen. It might make flying more frightening, but it's the best way to make it safer.
For a transcript, send $3 to Nova, Box 1000, Boston, Mass. 02118. Be sure to include the show title and allow 6 weeks for delivery. Major funding for Nova is provided by this station and by other public television stations. Additional funding is provided by grants from TRW and the National Science Foundation.